friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show a simple heat transfer analysis using SolidWorks flow simulation. In this example, I'll show all the different phases of heat transfer like conduction, convection, radiation through a basic example of Thermo-flask. Modeling of inner and outer part of the Thermo-flask has already been made. Let's start the assembly part of the components. We're selecting the outer case and the inner part. This one is the inner part and this is the outer part. Actually, this one should be fixed, so we'll make it fixed. And the inner part will be floating. Okay, these are the parts, right? And you can see inside this part we are having some kind of like spiral or spring. On the spring, this inner part will be resting. Let's make it a little bigger for understanding this one. Some spring is there. On the spring part, this one will be resting. Okay. And before assembly, we can provide some color to this one. Let's provide some color to the inner part. And appearance to this one, we can provide something painted and polished, sprayed, painted. Let's provide this red spray over this model. And this one should be transparent. Okay, now let's start assembly. Met, and for mating here, the different planes or axes should be aligned together. We are taking the front plane of the inner part should be meeting with the front plane of the outer part. So one constraint is satisfied. Now it is select the right plane of the outer part should be meeting with the right plane of the inner part. Green check. Two constraints are met. We have to select the third constraint. So we can drag it a little bit up. Now for selecting the faces, we can make it a little bigger. Now we have to select the face of this one should be meeting with the face of the inner Thermo-flask. Done. So green check. We got our model ready for analysis, right? We'll see it. This is the model, right? For better understanding, we can have a cut view of this one. We can cut it from the front plane. Green check. This is the model. We can see in a bigger way. So this is resting on the spring, and outside this Thermo-flask, one gap we have created. That gap will be working as a radiation medium. This one will be completely vacant. So from outer surface of this Thermo-flask, radiation will be occurring. Right? This is our model. Okay, fine. Let's take the complete view of this model. Is ready for analysis. Now for flow simulation, we have to create a closed volume, and that closed volume can be created with the leads. You can start with the leads with the flow simulation tools, create leads. And for creating leads, we have to select the surfaces. We can select the top surfaces for creating the lead. We select that face So lead is made. Green check. You can see lead 3 and lead 4, 2 leads have been created, right? Okay, fine. Next, we have to start analysis, and for starting the analysis, you have to create the flow simulation environment, and that can be done with the wizard itself. Now we will start with the wizard itself. By default, project name we are keeping as project 1, and unit system we are keeping as SI system, and temperature we will consider as degree centigrade. Next. Now here in this case, you can consider internal or external analysis depending on our requirement. If we are concentrating on the flow patterns of the inner side, we can go for internal analysis, and if we are bothered about the external surfaces, we can go for external analysis, right? So in this case, let's select external analysis, and inside this thermo-flask, one cavity has been created, and that cavity should be excluded for flow conditions. That means we want to provide a complete vacuum space inside this thermo-flask. So exclude cavities without flow conditions, and it will be heat conduction in solids, and as air will be outside this thermo-flask, so heat conduction in solids only, will not check this one. And again, radiation will be occurring from inside the thermo-flask surfaces, and environmental temperature we are considering as 20 degrees centigrade. Let's select the direction of gravity. Gravity will be in the y direction, right? So the value of G will be minus 9.81 in the y direction, and in the z direction it will be 0 value. Next, gases we are considering only air, as it is an external analysis, outside air will be there. Next, for this thermo-flask, we have to select two different materials. Inside we will provide glass, and outside we will provide alloy steels, right? So we are selecting two material. As a default material, we will take glass only. Let's select glass as a inside material, default material, and default wall radiative surfaces we will consider as non-radiative, and actual values will be provided during application of boundary conditions. Next, temperature we are considering as 20 degrees centigrade, and definitely solid parameter also same, it will be 20 degrees centigrade. So finish it. You can see this is the domain. The domain volume is very big. We have to make it little smaller to minimize the calculation timings. So computational domain, make that domain little bit of smaller. So our computational domain is ready. Green check. We can hide this domain. Next one, we have to apply the materials to this thermo-flask. Solid materials, insert solid material, predefined, glasses and minerals. We will select glass for the inner material. So we will select the inside surface. The inside component should be made up of glass. Green check. And again, for the outer part, we have to make with some other material. Solid material, insert solid material, predefined. Let's select the outer surface as alloy steels. Stainless steel 321 for the outer surface. So we have to select that outer surface also. We have to select the outer part. This is made up of stainless steel 321. Green check. So material is applied on both the components. Now for the lids, we can provide some material. Solid material, insert solid material, predefined, glasses and minerals. You can provide insulator for the lids. So we have to select the lids. Lid 3 and lid 4 both are selected as insulators. So we have applied our materials for this thermo-flask. Next one, we have to apply boundary conditions. Now for better application of boundary conditions, it is always suggested to have a segmented view of the model. So we'll cut it along any specific plane as per our requirement. Green check. We have taken the model in a segmented view. This is the model. Okay. Now we have to apply boundary conditions. So what we'll do is boundary conditions, insert boundary condition. As it is an external analysis, so from outside air will be showing, and inside surface we are planning to provide a temperature of 100 degrees centigrade, right? So it will be from the surface of this inside, so inside part of this thermo-flask will be having temperature of 100 degrees centigrade. So let's select walls, it is real wall, and temperature of the walls we are considering as constant temperature of 100 degrees centigrade. We have to select the face, so we can select tangency. So all the parts inside this thermo-flask have been selected with a constant temperature of 100 degrees centigrade. Green check. So inside this thermo-flask, initially it will suffer conduction. We can select these surfaces. So from here to here it will be conduction, and from this place to that place it will be radiation, as in between this place complete vacuum is there, and again from here to here it will be conduction, and finally from this place to the outside atmosphere it will be convection. So we'll repeat it again. Inside we are maintaining a constant temperature of 100 degrees centigrade, therefore from this place to that place it will be conduction, and again from this location to that location it will be radiation, as inside this one we are having complete vacuum, and again from here to here it will be conduction, and finally from here to the outside surface it will be convection. So we are having all the phases of conduction, convection and radiation. Okay, done. So next one we have to apply the condition for radiative surfaces. We have to provide radiation, right? So let's select the object in a bigger way. Radiation should be provided. So radiative surface, insert radiative surface, predefined. We want black body radiations from one wall to another wall. Instead of that we can put some kind of specific emissivity in between these two surfaces. In this case we are considering completely black body. From here to here it will be radiation. So select these phases, select tangency. So all part is selected. Again here also select tangency. So all the curved surfaces of this thermo-flask is selected. Green check. Now another boundary condition is required, that means from outside of this flask it will be having convection. So convective heat transfer coefficient should be provided at the outer wall. Boundary conditions, insert boundary condition, walls, it will be real wall. For the outer case, outer surface we are providing convective heat transfer coefficient equal to 70 watt per meter square degree Kelvin. For the outer surface, select tangency, done, and temperature outside it will be 20 degrees centigrade. So green check. Convective heat transfer property at the outer wall also provided, right? So we are having three different modes of heat transfer, that is conduction, convection and radiation, all the three phases. Next one, you have to select some goals, that is surface goals are required. Select insert surface goals. We want to have temperature at the outer surface of this thermo-flask. By the same time inside vacuum spaces also we have to select some goals. We'll select some specific goals. Initially we are bothered about the temperature at the outer surface of this thermo-flask. So it will be average temperature solid at the outer face of this thermo-flask. Green check. We can rename this one as average temperature of outer wall. Done. Two more goals we want to have, that means at two different faces, here and here also want to find out temperature of solid. So again goals, insert surface goals, it will be average temperature of solid. For proper selection we will make it little bigger. Select tangency, green check, and we can rename this one as average temperature at stainless steel inside. Done. Now another goal is required, that means you want to find out average temperature at the outer surface of this thermo-flask here at this location. Okay, and goals, surface goals. It will be average temperature of solid, let's select the surface, select tangency, green check, and let's rename it as temperature at glass outside. Done. Now another goal we want to have, that means we want to find out how much amount of heat is transferred because of radiation. That means we want to find the difference between the temperature at this location and at this location. So it will be in the form of equation goals. Insert equation goal, and it will come from the goals itself. So we have to find the difference of these two. Average temperature at glass outside minus average temperature at SS inside. Green check. Done. So we have selected 4 different goals. Now we can run this study. Let's run it. The solver window has started iterations. It will take some time for getting all these results. Whenever it is finished, we'll see the results and analyze it. Okay. The solver has finished its calculations. You can see the results here itself. Equation goal values we got in 72 degrees centigrade, and average temperature at stainless steel inside is 26.4 degrees centigrade. Average temperature at the glass outside is 99.28 degrees centigrade, and average temperature at the outside walls, that means from the convective surface, it is 26.4 degrees centigrade. We'll analyze all these things while seeing our results later on. Okay, let's close it, and we can see our results in the form of cut plots. Results, cut plots, insert cut plots. What is the temperature of solid? Temperature of solid distribution, you can see inside surface temperature is red zone, that means 100 degrees centigrade, and outside it is blue zone, that means in the range of 25 to 32 degrees centigrade, etc. Right? This is the cut plots. Let's hit fluid temperature. Green check. So outside it is completely blue. We can see the temperature at the outer face of this Thermo-flask, where convection is occurring from outer surface to the atmosphere. The temperature is in the range of 38 to near about 50 degrees centigrade. Okay, let's see this one in the form of animation. Cut plot 1, play. You can see temperature of solid also. Let's clear and hide this part. And want to see surface plots throughout all the surface. Use all faces to get surface plots, and want to see temperature of solid. That means you can see outside the surface temperature is in the range of blue zone, that means 25 to 30 degrees centigrade temperature, right? Let's see temperature of fluid. Outside this surface we are having air, so we can see the temperature of fluid equal to again in the range of 20 to 38 degrees centigrade, right? Now we'll see our results in the form of goals. That means goal plots. We want to see goal plots, insert goal plots. We see all the goals, show. Now it is showing all the results. First one is average temperature of outer walls. That means from which convection is occurring, it is 26.41 degrees centigrade. Minimum value is 26.41. Average temperature at the outer face is 26 degrees centigrade, whereas the temperature of air was 20 degrees centigrade. Atmospheric temperature was 20 degrees centigrade, and outside temperature of the thermo-flask is 26.41 degrees centigrade. Right? Again, we want to see some other things like second one, average temperature at stainless steel inside. That means next to this surface, temperature is 26.47 degrees centigrade. The outside surface of this stainless steel container is having temperature 26.41 degrees centigrade, and inside it is having temperature 26.07 degrees centigrade. Next one, the inside surface of this flask is having constant temperature of 100 degrees centigrade, and it is also having two faces. The temperature outside this thermo-flask is 99.28 degrees centigrade, and the difference of temperature in between these two is equal to 72.81 degrees centigrade. It is not actually the heat transfer rate, it is actually the temperature difference because of radiation. 72.81 degrees centigrade temperature difference because of radiation. Now these things you can see in the form of history also. It will be in the form of graphs. Like you can say average temperature of outside walls, initially it was 20 degrees centigrade, and after 14 numbers of iterations its temperature is 26.41 degrees centigrade. Similarly, average temperature of stainless steel next to the outer surface, the temperature is 26.47 degrees centigrade. And similarly, average temperature at glass outside it is 99.28 degrees centigrade, and the difference of temperature in between these two equal to, you can see it is 72.8 degrees centigrade. These are the goals we obtained from our goal plots. If you want to have a detailed analysis, we can transfer all this data into Excel and go for detailed analysis. Okay. Instead of stopping it here, we can go for further optimization. The temperature difference in between these cavities is equal to 72.8 degrees centigrade. We can optimize this temperature by changing the input variables, form of thickness of these glasses, or we can say the boundary conditions, that means temperature of the inside the wall also we can vary, right? So in this way you can go for optimization. Okay, so this is today's basic analysis showing an example of conduction, convection and radiation with a very simple example of thermo-flask. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.